So I'm sharing my screen. Yeah. So my screen is visible, right? Okay. So asynchronous counters will discuss. Okay, counters are nothing but it will it are used it will be used to count the number of clock pulses. Okay, so suppose example, if you take any electronic voting machine. Okay, electronic voting machine, there is a EVM machine, and as well as there is a ballot box. Okay, parallelly it will print the slip. So after completing the voting, they will count this count, and they will count the number of slips, and they will sing, they will match. Okay, when there is it is matching means that means the voters, whoever the voters are there, that same thing, it is matching like that. And also in the shopping malls also, entrance, there will be counter will be there, up counter will be there. So after end of the day, they will compare with the number of tickets sold, and this counter. Okay, and down counter also, when you are launching any rocket. Okay, so that means that they are down counting from 10 to 0, they are counting. Okay, so that is there we can use down counting. Okay, so these are some applications of counter. So basically counters are two types. So one is counters. So counters means basically simply it will count the number of clock pulses. Okay, it will count the number of clock pulses. Okay, so here again, counters are divided into two types. Those are synchronous counters and asynchronous counters. Okay, so counters. Okay, so one is asynchronous counter, and synchronous counter. Okay, so asynchronous counter is nothing but what, the output of one flip flop is acting as a clock to the next flip flop. Okay, so that means one flip flop will trigger. So when you are getting the output of one flip flop, then only it is acting as a clock for the next flip flop. Okay, whereas synchronous counter means common clock will be there. Okay, common clock will be there for all the flip flops, and again passage of clock and negage of clock will be there. Okay, so today our discussion is about the 2-bit asynchronous counter. Okay, our discussion is 2-bit asynchronous counter. Okay, what is this 2-bit asynchronous counter? So let us take so basically for the counter, we can use T flip flop and JK flip flop. Okay, JK flip flop and T flip flop for designing this counter. That operated in which mode means a toggle mode. So yesterday we discussed about JK flip flop, no? So when it is a toggle mode, when J equal to K equal to 1, then you are getting Qn plus 1 equal to what? Toggle state. So this is Qn bar. Okay, and when T equal to 1 also, you are getting the next state, that is Qn plus 1 equal to what? Qn bar. Okay, so this is nothing but toggle state. Okay, so basically those are operated in toggle state. Okay, we are using JK flip flop and T flip flop, that too operated in toggle mode. Okay, so here if you see, so I'm designing the 2-bit asynchronous counter by using JK flip flop. Okay, so that means there is a mod of the counter. So mod of the counter. So 2-bit counter means it will count from 0 to 3. Suppose if it is a n-bit counter, it will count from where to where? 0 to n minus 1 it will count. Okay, so this is you can say that mod 4 counter. Okay, so how to find out the number of flip flop? This is the formula. N is less than or equal to 2 power n. Okay, suppose if you want to design mod 7 counter, so 7 is less than or equal to 2 power n. Suppose if you take n equal to 2, so 7 is less than or equal to 4 means this is not satisfying. Okay, so if you keep n equal to 3, then 7 is less than or equal to 2 cube, 7 is less than or equal to 8 means this is satisfying. So this will decide, means from this formula I can decide that how many number of flip flops I can use for designing the counter. Okay, this is the formula you need to use. Okay, n is less than or equal to 2 power n. Okay, n is less than or equal to 2 power n. Okay, and next, so here I am designing 2-bit asynchronous counter. No, so I am using this 2 JK flip-flops. Okay, so 2-bit counter. So for n-bit counter you need n flip-flops. For 2-bit counter you need how many flip-flops? 2 flip-flops. So here for 2-bit counter you require 2 flip-flops. Okay, so this is 2 flip-flops, 2 flip-flops. Okay, and so here you have J1, K1, Q1, J2, K2 and Q2, J2, K2 and Q2. Okay, so J1, K1, so J1, K1, so I told you, no, so this is operated in which mode? Toggle mode. Toggle mode means J1, K1 are connected with what? J1, K1 are connected. So here J1, K1, okay, J1, K1 and J2, K2, J2, K2, these connected both, and these both are connected to toggle state. Okay, these both are connected to what? 1. Okay, J1 equal to 1, K1 equal to 1. This is connected to logic 1. So then these two are operating in which state? Toggle state. Okay, and next, so you are giving, suppose passage of clock. You are giving passage of clock. Okay, so passage of clock, this is clock, this is clock, and when you are giving passage of clock, so this Q1 bar is acting as a clock for the next flip flop. Q1 bar is acting as a clock for the next flip flop. Okay, so this is passage of clock. Okay, so so here basically this is which counter means we can call this as ripple counter also. Asynchronous counter we can call as a ripple counter also. Other name for asynchronous counter is ripple counter, and I am designing which counter means up counter. I am designing up counter. Up counter means it will count from where to where? 0, 1, 2, 3. After that it should come to 0. Okay, this is up counter. Okay, so basically like so here so passage of clock means what? Like this is a clock, this is the clock. So during this passage of clock, during this edge, when it is going from 0 to 1 only, then this counter will activate. Okay, so this is nothing but passage of clock. Okay, here I will write the table. So let us take clock, and next Q2, Q1. Okay, Q2, Q1. So suppose clock 0 is given. Okay, clock 0 is given. So here what you are getting initially, the output of 2 flip-flops will be what? 0, 0. Okay, output of 2 flip-flops will be what? 0, 0. Okay, so let us take these 2 flip-flops are 0, 0. Okay, so during 0 o'clock, 2 flip-flops will be 0, 0. Okay, and next you are applying first clock. First clock, when you are applying first clock, what happens? This clock is given to first flip-flop. Always yeah, that means you need to remember the rightmost bit is MSB bit and the leftmost bit is LSB bit. Rightmost bit is MSB bit and leftmost bit is LSB bit. The LSB of the flip-flop is always toggle. Okay, always toggle. So here during this first clock pulse, what happens? Initially this is 0. This will toggle from where to where? So this will toggle from 0 to 1. Okay, always it will toggle. So here this is complement. That means this is 0. This becomes what? 1. This becomes 1. So when it will toggle from 0 to 1, so this becomes what? 0. This becomes 0. Okay, so that means so this is acting as a clock for this flip-flop, no? So this is flip-flop 1 and this is flip-flop 2. Okay, so this will be toggle. When it will be toggle? During the passage only it will toggle. So but here it is transition from 1 to 0. Okay, it is transition from 1 to 0 means negate of clock. So negate of clock means what? It will be in the same state. It will be in the same state. So it will be 0 only. Okay, so that means at first clock pulse, so MSB is what? Q2. Q2 is 0 and Q1 is 1. Q1 is 1. Okay, and at second clock pulse, what happens? Again always it will toggle, no? So it will toggle from where to where? 1 to 0, and again it will so it is changing to 0 means it becomes what? 1. Okay, it becomes 1. So So here you got 1 0 to 1 0 to 1 1 means what? Passage of clock. So passage of clock means it is acting as a clock, no? So it is acting as a clock means so you got the passage of clock, so this will trigger, so this will change from where to where? 0 to 1, 0 to 1. Okay, so at second clock pulse what happens? It is changing, so that means Q2 becomes 1 and Q1 becomes 0. Q1 becomes 0. Okay, like that. And next you see at third clock pulse what happens? Always this flip flop will toggle, so this becomes what? This becomes 1, this becomes 1, and this becomes what? 0. Okay, this becomes 0. So this is a negate of clock. So negate of clock means what? This is negate of clock. So it is going from 1 to 0. This is negate of clock. So what happens? So it will be in the same state only. So that means it will be in 1 only. Okay, so that means at third clock pulse it becomes what? 1 1. Okay, it becomes 1 1. Okay, my screen is visible, I think so. Okay, yes, so it becomes 1 1. Okay, at third clock pulse what happens? It becomes 1 1. Okay, and next at fourth clock pulse I want to check. Okay, at fourth clock pulse what happens? At fourth clock pulse let us take this is fourth clock pulse. It is triggering from where to where? 1 to 0. It is triggering from 1 to 0, and it will change from 0 to 1. It will change from 0 to 1. Okay, so 0 to 1 means it is passage of clock. This is passage of clock. So during this passage of clock, this will also toggle. So it will toggle from 1 to 0. Okay, at fourth clock pulse what happens? So Q2 becomes 0 and Q1 becomes 0. Q1 becomes 0. So how you got? So first, so initially, so if you draw the state diagram, so initial state is 0. First clock pulse, it is going from where to where? 0 1. Okay, next state. And second clock pulse, it is changing from 1 to 0. Okay, and third clock pulse, it is changing from 1 1. Okay, third clock pulse, and fourth clock pulse, it is coming to the initial state. Okay, so like this you can understand the operation of asynchronous up counter, asynchronous or ripple counter, that is up counter. Okay, so up counter, it is counting from where to where? 0 1 2 3, and after that it is coming to the initial state, that is 0. Okay, so this is 3-bit asynchronous counter. And next I will design 2-bit asynchronous down counter. Okay, is there any doubts or any queries in this, so that I will move forward? Any doubts or any queries in this 2-bit asynchronous counter? Anyone? Shall I move forward? Okay, so see here, next I will design 2-bit. Next I will design 2-bit asynchronous or ripple down counter. Okay, so asynchronous ripple down counter. So if you see, so that means what is the change? Once again I will draw the diagram. So I am using which flip flop? JK flip flop. I am using JK flip flop. Okay, so I am using JK flip flop. Two flip flops. 2-bit means what? 2 flip flops I am using. Okay, as the LSB of the flip flop will always toggle, and the output of one flip flop is acting as a clock for the next flip flop. So this is what J1 K1 connected together, and J2 K2 also connected together. Okay, and these both are given to one logic 1. Okay, toggle state. So flip flop 1 and flip flop 2, and here directly the passage of clock is given to first flip flop. Okay, passage of clock is given to first flip flop, and here you have Q1 and Q2. Okay, so here in down counter what happens, Q1 is acting as a clock for next flip flop. Q1 is acting as a clock for next flip flop. Okay, this is Q2. Okay, so anyway the rightmost flip flop, this is MSB of the flip flop and this is LSB of the flip flop. So LSB of the flip flop will always toggle. Okay, always toggle. So here I'll write the table. So clock next Q2 and Q1. So at 0 clock what happens, initially the output of two flip flops will be 0 only. Flip flops will be 0 only. Okay, so 0 0 0 0, let us take 0 0 at first clock pulse. At first clock pulse what happens, okay, at 0 clock pulse both are 0 0 only. Okay, at first clock pulse what happens, at first clock pulse, so this will toggle. So this will toggle from where to where, 0 to 1. Okay, so as this is toggle from 0 to 1, this is passage of clock. Okay, so that means passage of clock means what, it should trigger from 0 to 1. Okay, so this is passage of clock. Okay, passage of clock, and so this will also toggle. So this will also toggle. So this becomes what, 1 1. Okay, at first clock pulse it becomes what, 1 1. At first clock pulse it becomes 1 1. Okay, and next at second clock pulse, we'll see. Okay, at second clock pulse again this will toggle from where, always it will toggle for every clock edge. Okay, so this will toggle from 1 to 0. Okay, this will toggle from 1 to 0. Again this is neg edge of clock. Okay, so this will toggle only during the passage of clock, but here you got neg edge. 1 to 0 means nothing but neg edge. Okay, so it will be in the previous state only. Okay, it will be in the previous state only. So that means here you are getting 1 0 1 0, and next at third clock pulse we'll see. At third clock pulse again it will toggle from where to where, it will toggle from, one second, yeah, it will toggle from here it will toggle from 0 to 1. Okay, it will toggle from 0 to 1, and this is passage of clock. Okay, this is passage of clock. So during this passage of clock again, this is passage of clock means it will toggle. Okay, here during third clock pulse what you will get, 0 1 0 1. Okay, and next at fourth clock pulse, you see, at fourth clock pulse this will toggle from 1 to 0. This is neg edge of clock. Okay, and neg edge of clock means what, this will not trigger. Why? Because you are getting neg edge of clock. Okay, so that means it will be in the same state, 0. Okay, so at fourth clock pulse what happens, at fourth clock pulse you are getting 0 0 0 0. Okay, so that means I can draw the state diagram. So first let us take the initial state. What is the initial state? Initial state is 0 0, and it will start from where, 1 1. 1 1 means first clock pulse it will come to the first 1 1. Okay, and next second clock pulse it will come to 1 0. Okay, at third clock pulse it will come to 0 1. At fourth clock pulse it will come to the initial state. Okay, so like this it will count. So that means 0, next 1, sorry, 3, next 2, next 1. After 1 it will come to the initial state. After 1 it will come to the initial state. Okay, so this is the 2-bit asynchronous counter. Suppose if it is neg edge of clock. Okay, so neg edge of clock, so that means if it is passage of clock, when I am designing the up counter, I given Q bar as a clock to the next flip flop, no, and if it is down counter, I need to give Q1 as a clock to the next flip flop. Okay, I need to give Q1 as a clock to the next flip flop. Okay, so here if it is neg edge of clock, okay, if it is neg edge of clock, just vice versa. Suppose if you want to design up counter, so Q1 is acting as a clock to the next flip flop. Okay, Q1 is acting as a clock to the next flip flop. Okay, and if it is down counter, Q1 bar is acting as a clock to the next flip flop. Okay, clock to the next flip-flop. Next flip-flop. Okay, so this is about asynchronous counter. So next I am going to for the programming. Okay, I wrote the programming for asynchronous up and down counter, and I will both passage and negate I wrote, and I will explain you this passage and negate of the counter. So I'm opening this Xilinx Vivado. 1 second. Okay. One second, it's opening. I wrote the program. Yeah, it's opening. Yeah. Okay. This one I'll close. Counter new. Okay, this is a counter new. So if you see here, yeah, it's opening. Yeah, asynchronous. Yeah, asynchronous counter. Okay, asynchronous up counter. Okay, this is asynchronous up counter. Okay, I wrote the program for asynchronous up counter. Okay, so if you see this one, asynchronous up counter. So here, 1 second. Yes, see here. So that means module asynchronous up down counter. I am designing the asynchronous up down counter. So input wire clock and input wire reset. So basically in the industry they will represent separately for these input declaration. Why? Because suppose if you are declaring in the same line, suppose 100 inputs are there. So we can't accommodate in this line, no? So that's why separately we need to accommodate this input separately. Input wire clock, input wire reset underscore n, and input up down, input wire up down. Okay, and next output. So I'm using behavioral modeling. That's why I'm using reg, and I'm using the vectors. Vectors is 1 down to 0 count. Okay, 1 down to 0 count. So always at the rate what this is, I'm using asynchronous active low reset. Okay, how I can use asynchronous active low reset? So in the sensitivity list I need to use passage of clock or negate of reset begin. Okay, begin if not of reset. Okay, if reset equal to 0, so what I am doing, I'm initializing count to what 0. Okay, else begin if up means if up down. Okay, if up down equal to 1. Okay, so this will be chosen for we can call as a mode like that. Okay, if mode equal to 1 it is acting as up counter, if mode equal to 0 it is acting as down counter. So up down, so if it is up down equal to 1, so count equal to what, count plus 1, else count equal to count minus 1, end. Okay, so where I need to, so this begin is there, no? So begin I need to end, and after that this begin also I need to end, and end module. Okay, so this is the program. After that I need to write the simulation, no? So here if you see the simulation, so here up down counter, right click, set as stop. Okay, this is up down counter. I wrote the test bench for this. So module, and this is my module name, tb underscore asynchronous up down counter. Whatever the input variables variables are there, that I need to initialize with the reg data type, reg clock, reg reset underscore, and reg up down. Okay, whatever the outputs are there, that I need to initialize with the count, and 2 bits are there. That's why I'm using a vectors concept, 1 down to 0, and I need to instantiate. Okay, how I am instantiating, that means my instance name. Okay, what is my instance name? Asynchronous underscore up down underscore counter, and UUT is nothing but unit under test, and whatever the variables outside this bracket are nothing but design variables, inputs and outputs, and whatever the variables inside the bracket are nothing but test bench variable, test bench inputs. Okay, so initially I given the test bench inputs, no, those will comes in the bracket. Okay, and I am generating the clock. Okay, initial clock equal to 0, I am initializing the clock, and always #5 clock equal to not of clock. So that means this is a half cycle. #5 is nothing but for half cycle. I need to make a complement. Okay, so total clock period is nothing but 10 time units. Okay, so 10 time units, 10 nanoseconds I am generating the clock. Okay, so if you are using like EDA playground, you need to use these two functions and initializing the values. Okay, so first I am applying the reset. I am making up down equal to 1. Okay, after that again I'm applying, I'm releasing the reset. Okay, for 10 time units I'm releasing the reset, and next for 50 time units I am doing up counter, and next 50 time units I am doing down counter, and after that for 20 time units I am again applying the reset. For 10 time units again I'm releasing the reset. Okay, and finally for 40 time units I am seeing the up down counter. Okay, up down counter, so up counter I'm seeing up down equal to 1 means I'm seeing the up counter. So after 20 time minutes I'm finishing the simulation. Okay, so this is the test bench. Okay, so I want to simulate this. Okay, so you can elaborate the design also. So for elaborating the design, so here this should be top module and this should be top module, and you can see the how the compiler is making this netlist. We can see in the elaborated design. Okay, just I'm elaborating the design. Yeah, so this is my design. Okay, so like this I am getting through two adder circuits, and here through mux, and I am using this is for up counter and down counter, and this is nothing but D flip flops. Okay, you are using say the D flip flops. Okay, for this. Okay, so this is my schematic or netlist. Okay, I want to simulate this design. Go to simulation and run the simulation, run the behavioral simulation. Okay, so I want to see the output for a 2-bit asynchronous counter. So if you see this, so see here, so if you see the waveforms, fit to page, so see here, so that means during this reset, here reset is what? Reset is activated, so counter initial values are 0 only. Okay, when it is going from reset mode to functional mode, so immediately you are not getting the output. When you are getting during next passage only, you are getting the output. See here, during next passage, so that means reset removal is synchronous. Okay, reset removal is synchronous. Okay, during this synchronous, this is during this passage of clock only, the count is incrementing 0 1 2, and after that 3. Okay, this is 2-bit counter, no, 0 1 2 3. After that it is becoming 0. Okay, so like that it is counting 0 1 2 3, 1 2 3, and after that it is making as 0. Okay, so again it is starting 0 1 2, and here what happens, here 0 1 2, again 0 1 2 it is counting, and here you see, so that means again you activated the reset. Okay, so reset applied is what? Asynchronous. Okay, irrespective of input and clock, it will force the output to 0 only. Okay, it will force the output to 0 only. So here this is nothing but it is going from functional mode to reset mode. Okay, so functional mode to reset mode. Again, when it is going to reset mode to functional mode, this is synchronous with the clock. Okay, immediately it is not, you are not getting the output. Okay, when you are getting means during this passage of clock only you are getting the output. Okay, during this passage of clock only you are getting the output. Okay, so like this you can analyze. So during this passage only you can get the output. Okay, this is about the counter asynchronous active low, active low reset counter. Okay, and passage of this is nothing but a positive edge trigger. Okay, so negative edge trigger also. So negative edge trigger, just set a stop, and this is also negative edge trigger, set a stop. Okay, set a stop, and this is neg edge. Okay, neg edge of, so that means whole thing is same only. So in the while, one second, so in the while, one second, yeah, second, how much is my charging? Okay, one second, just 1 minute, I will bring my charger, just 1 minute. Okay, yes, so here this is up counter and down counter I designed. Okay, and next, one second, my voice is audible, no? Okay, yes, next I want to design asynchronous, which one, neg edge of clock. So what is the difference? So all are same only in the always block. Okay, in the always block, wherever the sensitivity list is there, in place of passage of clock, what I am giving, I am giving neg edge of clock and neg edge of reset. Okay, this only the change I am giving. Okay, whole program and test bench all are same only. Okay, so just I am simulating this. Okay, I am simulating this. So see here. So just I want to see the simulation. One second. See here, fit to page. So here if you see, so when the reset is what, when reset is 0, okay, when reset is 0, what you are getting, that means the output of this counter becomes output of counter becomes 0 only. Okay, output of counter becomes 0 only. And when reset is 1, okay, immediately you are not getting the output. When it is going from reset mode to functional mode, immediately you are not getting the output. When you are getting, you are getting at the neg edge of clock. You are getting at the neg edge. Why? Because in the sensitivity list I given neg edge of clock and neg edge of reset. Okay, so that means neg edge of reset means active low reset. Okay, and during this neg edge also, the counter will count from up count. It is acting as up count. Okay, so here also it is acting as up count 1 2 3. Okay, here it is acting as up count. Okay, again it will start. Okay, during neg edge of clock 0 1 2 3. Okay, and 0 1 2 3, and here also up count 0 1 2 3. Okay, 0 1 2, and here so it will start from 1 0, and here what happens, here reset becomes what, 0. So reset is activated. So reset is activated means what, so the output becomes 0, and when it is going from reset mode to functional mode, immediately you are not getting the output. Here I am using as a down count. Here up to here we are using as a up count, and here I am using as a down count. See here. So during this neg edge of clock, what happens, it will start from 3 2 1, and after that again it will start from 0 1 2, it will be up counter. Okay, so like this you need to analyze the waveforms for up down counter. Okay, so up down counter, that is synchronous asynchronous active low reset. One is passage of counter, passage of clock, and next is negate of clock. Okay, this is asynchronous counter. Okay, so this is about today's session. Any doubts or any queries?